All right, class, now we're finally into the middle section of Chapter 5, where we're going to look at this new idea of factoring, okay? Factoring. Now, we've already learned that we've got to look for a GCF. That's rule number 1 of factoring. We got to check for a GCF. And now we're going to look at some special patterns. Some special patterns that will help you tremendously if you memorize them and be able to recognize them. And when we get into section 5.5, we're going to look at this new pattern called difference of squares. Now, I'm used to calling it difference of perfect squares. Okay, so if you look at my first slide, if I have the binomials a plus b and a minus b, those binomials are called conjugates. Do you recognize that we have the same letter, A and A? We have the same letter in the back position, B and B. What's different is the signs. One is a plus sign and one is a minus sign. I like to call this one the sum and this one the difference. All right? And so we're going to see when I multiply those together, I'm going to get a binomial a squared minus b squared. Now, here's what I mean. Let's say I had x plus 3, and let's say I had x minus 3. Okay? Now, if we're going to multiply those, let's use the mental method that we learned last week. We're going to FOIL it. And so that means x times x is what? X squared. And then O's for outside. So that's going to be the guys on the end, negative 3 and x. And then inside the two right beside each other. And then last, 3 and negative 9. Did you notice what happened to my middle? Yes, because one is a plus sign and one is a minus sign, the middle always cancels out. So if you can recognize that you have conjugates or sum and difference, then you say, oh, when I FOIL that, the middle's going to cancel out, and you don't have to do it if you've got that memorized. Now, let's see what that means as we look at a couple of these problems. It says write each product as a binomial, okay? So that means 2 terms, okay? So if we use FOIL, but we look up there and say, hey, wait a minute. Those are conjugates. That's sum and difference. I have M and M. I also have 8 and 8. What's different is the signs. This is my sum. This is my difference. And if you can recognize that you have that you have conjugates, then we don't have to FOIL. We can say, oh, because they're conjugates, the middle's going to cancel out. So we would just say m times m, which is m squared. And then we would have 8 times 8, which is negative 64. But again, you've got to be able to recognize that you have conjugates or sum and difference. So let's look at number 2. Did you notice we have 8x and 8x? We have the same constant, 11 and 11. If you look, they're conjugates. This is the sum and this is the difference. And so once I recognize that I have conjugates, one is plus and one is minus, the sum and the difference, I know that the middle's going to automatically cancel out, so we can just multiply 8x times 8x, which is 64x squared, and then negative 11 times 11 is negative 121. But again, here's the time in math where we got to start memorizing some things to be ready. Okay, let's look at our next slide. Let's try a few more. Yeah, as soon as you recognize, oh, conjugates, this is the sum and this is the difference, we know the middle's going to cancel out, so we're just going to say 7 times 7, which is 49, and then 2a times negative 2a is negative 4a squared. Let's do it one more time. Do you recognize? Do I have conjugates? Do I have sum and difference? I sure do. So 3m times 3m squared is going to be 9m to the 4th. Negative 8n squared and negative 8n squared is negative 64n to the 4th. Okay, so pretty simple if I recognize, oh, exact same letters, exact same numbers. One says plus, one says minus. Mrs. Burton calls them sum and difference. Also recognizing their conjugates, done deal. Now, algebra is very good about going forwards and backwards, and so now we're going to learn how to go backwards. Can you look up here and figure out what pattern's taken place? What pattern is taking place? Okay, if this is number 1 and this is the second number, this is the third number, this is the fourth number in my sequence, what did I do to the blue number to get the top number in black? Do you realize what's going on? Yes, good job. 2 squared is 4, 3 squared is 9, 4 squared is 16. So what's my next number going to be? Yeah, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, then we've got what, 100, and then what, 121, and 144, and then it's 169 and 196, and then one more. Okay, so these are our perfect squares. Now, if you remember a few weeks ago, I said it'd be a good thing to memorize your perfect squares and cubes up to about 20. Now they've got us doing the reverse. They want me to factor, okay? Write as a product, a binomial times a binomial. That's what they want. So if I look there, well, the first thing I'm going to check for, always and forever, I always look to see if I have a GCF. Remember, that was chapter 4 ago. So if I look up here, if I look at number 1, well, I don't have a GCF. But did you notice there's only 2 terms? Remember when we looked at our quadratic equations, remember there was always a quadratic term, and then we had a linear term, and then we had a constant term. And if you notice, there's no constant term. There's only 2 terms. So that means that the middle term canceled out. So when I look here, I say, oh, this is one of my special patterns. It's called difference of perfect squares. And if I look here, what can I multiply by itself to get that? Well, this is going to be m plus 5, and this is going to be m minus 5. We're going to see that difference of perfect squares is the inverse or the opposite of multiplying conjugates, or my sum and difference. Because what happens here, remember, we saw if I have the exact same letters with the exact same numbers, one is the sum and one is the difference, that the middle always cancels out. So that's why I only have 2 terms. So if you look up here and we're factoring, okay, and there's no GCF, the second thing I'm looking for, if there's 2 terms, I want to check if it's difference of perfect squares. My little, okay? So if I look at number 2, oh, I don't have a middle. There's no linear term. So is this difference of perfect squares? Well, here's how we check. Is 9 a perfect square? It sure is. Is a squared a perfect square? It is. Is 10 a perfect square? It is. Now, for this to work, there's got to be a minus sign in between them because it's the difference of perfect squares. So if I can realize my front term is a perfect square and my back term is a perfect square and there's a minus sign in between them, this is difference of perfect squares. And to factor difference of perfect squares, I need the sum and the difference. So I like to say the square root of 9a squared is 3a. It's going to be 3a plus 10, and then it's going to be 3a minus 10. Okay, so again, it's recognizing patterns and memorizing what to do when. Let's look at number 3. Some factor. So I look, is there a GCF? Well, between 81 and 121, there's no GCF. There's only 2 terms. Are they perfect squares? Well, 81's a perfect square. Now, how do you know your exponent's a perfect square? Well, you know if the exponent is even, so n squared is a perfect square. 121 is a perfect square. And yes, we do have a minus sign in between, so this fits the category of difference of perfect squares. How do we factor difference of perfect squares? Oh, we need sum and difference. So this is going to be 9n plus 11, and that's going to be 9n minus 11. Okay, let's look at number 4. Do I have a GCF? Nope, no GCF. There's only 2 terms. Does it fit the pattern of difference of perfect squares? Well, negative 144 is a perfect square. We have a minus sign in the middle. My exponent is even, so that means that y squared is a perfect square also. So I need it to look like sum and difference. So here we go. 12 times 12 is 144, and we could say plus y, and then we could say 12 minus y. Are you seeing the pattern and how to memorize it? Now, let's look at number 5, throwing us a little bit of a curveball here, but that's okay. So if I look at number 5, we've got s to the 4th minus 16. So GCF, no GCF in number 5. Or is it difference of perfect squares? Well, my exponent is even, so that is a perfect square. 16 is a perfect square. We got the minus sign in between. So what 2 s's am I going to multiply together to get s to the 4th? Yeah, it's got to be s squared minus 4, and then it's going to be s squared plus 4. Now, they do this all the time in algebra, and we've got to train ourselves to look for this. But there is always, 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 we might have to factor again. We've got to make sure that we factor completely. So when I look up here, did you realize we actually have difference of perfect squares again? Yeah. S squared, that's a perfect square. We've got a minus sign in the middle. 4 is a perfect square. So to make sure I factor this completely, check back and make sure that one of your binomials is not difference of perfect squares again. So this is going to become s plus 2, s minus 2, and then we still have to bring the second binomial down from the original, and that's your final answer. Okay, let's look at number 6. If I'm looking at number 6, and I'm looking there, and I have 2 terms, but remember, don't forget rule number 1. When I look at number 6, do you realize right away that we have a GCF? Remember, GCFs can be numbers, and if I look between 2 and 18, well, I'm going to have to factor out a 2. But remember, GCFs can also be letters. So if I have a to the 4th and a squared, we're going to factor out an a squared. Remember, we take the lower exponent. So now I've got to go back and divide each term by my GCF. The 2's are going to cancel. A to the 4th divided by a squared is a squared. And then 18a squared divided by this is going to give me minus 9. Now let's look at the factors that remain back in our parenthesis. We got to make sure, hey, can I factor that? Well, we took out our GCF, but when I look at the factors that remain, did you realize that is difference of perfect squares? It is. We've got a squared minus 9. So to factor this completely, we bring down the GCF again, and then this is going to be a plus 3 and a minus 3. All right? And so make sure you can recognize the pattern, difference of perfect squares. Let's try another one. One more. Now, when I look at number 1, and I kind of train you to look for difference of perfect squares right away, oh, but that's not difference of perfect squares because 27's not a perfect square, 12's not a perfect square. Oh, don't forget about rule number 1. What's rule number 1? We always check for a GCF. And when I remember rule number 1, then I've got to realize, oh my goodness, there is a perfect square. There is a GCF. So between 27 and 12, if we're looking at the number part, what are we going to have to factor out? Yeah, we can factor out a 3. Now, let's look at the letters. We've got a cubed and a. Remember, we always factor out. If it's common to both, we factor out the lower exponent. So we're going to factor out an a. Did you notice both of my terms also have a b as well? So we're going to factor out the b. And then what's left? My factors that remain, well, we've got 27 divided by 3, which is 9. A cubed divided by a, which is a squared. And the b's would cancel. And then if I look at the second term, then we've got 12 divided by 3, which is 4, and then the letters cancel. Okay, so we took out our GCF, and then we're going to say, oh, the second thing I'm going to look at is my number of terms. And we have 2 terms, so we're going to check to see if it's difference of perfect squares. Difference of perfect squares. So let's look up there and see. Well, is 9a squared a perfect square? It sure is. Is 4 a perfect square? Yes, it is. There's a minus sign in between, so the factors that remain inside my parenthesis are perfect squares. So how do we factor difference of perfect squares? That's right. We go back and we do sum and difference. What number times itself will give me 9a squared? Well, that's going to be 3a. And then we're going to have, and 3a. We need one to say plus and one to say minus to get our sum and difference. And then it's going to be 2 because 2 times 2 is 4. Don't forget to bring that GCF back down. One more time. Let's see what we can do with it. If I'm looking at number 2, well, rule number 1 says GCF. Well, if I look, there's no number GCF, but I definitely have some letters that are GCFs. So if I look between x to the 5th and x, we're going to factor out the lower exponent. Between y squared and y to the 6th, we're going to factor out y squared. What are my factors that remain? Well, the 16 is going to come down, and it's going to be x to the 4th. And then, if you notice here, our x's would cancel when we divided, and we would have y to the 4th. Now, getting a little radical on us, we took out the GCF now. Do we have difference of perfect squares? Yeah, 16 is a perfect square. Both of my exponents are even, so they're perfect squares. So how are we going to factor that? Well, 4 times 4 is 16, and then it's going to be x squared plus y squared. Yeah, and then it's going to be 4x squared minus y squared. Now check it out. Have we factored completely? Let's make sure we factored completely. Now to check to make sure we factored completely, let's look at those factors that remain. And hopefully you notice, that's difference of perfect squares again. So final answer. We're going to bring down the x and the y. We're going to bring down the 4x squared plus y squared. And now we've got to factor this last one because it's difference of perfect squares again. We're going to have 2x plus y and 2x minus y. Okay, a lot of little things to pay attention to as we go through, but we're going to practice really hard memorizing, recognizing, and being able to factor difference of perfect squares. All right, class, you can start your homework.